Today we're going to look at expanding the Game Boy support to register transfer language, the intermediate language that Reko uses to perform analyses of machine code and turn it into high-level code. So before we jump in, we need to understand a little bit about what the register language, or RTL, is, and the reason and the rationale behind it. Now, let's do a little sketching. Every CPU has its own language, machine language, which is encoded as bytes. And then a disassembler turns raw bytes into something that humans can read. And that's very helpful for assembler language programmers who can understand these assembler instructions and make sense out of a program. But with large quantities of assembler language, it becomes more comfortable to use a higher level construct. However, assembly language does not map one-to-one with a higher level language like C or Rust. Especially in older architectures, there are a lot of extra things going on when you perform an instruction. As an initial example, we can take the add instruction of a CPU. So let's take the add instruction of the Game Boy CPU. It looks something like this in assembler language, and it does what it says. It adds B to A and stores the result in A. But it actually does a little bit more than that. If you look at what's actually happening in the processor itself, what it is doing is it's first computing this sum and storing that in A, but then it also is setting a bunch of condition codes. And the condition codes are dependent on the result in A. In this particular CPU, there is a flag that is called Z for 0, which is set if the result of the addition is 0. And there's another flag called C, which is the carry flag, which is set if the sum of the two unsigned numbers A and B overflows the 8 bits, and we have a carry out from this instruction. So this needs to be modeled accurately if you want to handle or turn this into a higher level language, because a lot of the instructions that are generated by a compiler or by an assembler language programmer make use of these condition codes. For instance, very typically you would find an instruction sequence like add AB, and then right after that you might want to check to see if if there was an overflow, then maybe you want to go to the overflow location in your program. And this implicitly looks at the bit flag C, the carry flag in the condition codes. So the the low level or the RTL representation of this would be something like test for overflow. Now this overflow is not a label, this is some internal, it's not a program label like this, it's more of a name for the state that we're checking for, and then we tell it where do we get the information about whether overflow has happened or not. And if this is true, then we want to go to the destination overflow, wherever that might be. So for instance, if this is address 1234, then this would be 1234. So the next job in order to support this architecture on this processor is to convert all of the instructions, including all of their little side effects, like the setting of the condition code registers, into the low-level RTL language. The RTL language is defined in the core project of Reko, and it's under RTL right here. So here are selection of instructions, and I'm going to go through the more important ones. There are a few extras, but they're documented. You can look at this at leisure. The most common one is RTL assignment, which clearly does an assignment or models an assignment between a source and a destination. The source can be a register, it can be an immediate or more complex instructions, and the destination can be a register or maybe a memory address. Here we have the branch instruction, which, as I just sketched, takes a condition, and it also has a destination. And that is because it's a subclass of the RTL transfer instruction, an abstract base class that handles all kinds of transfers. Now, transfers are any time the instruction pointer or the program counter changes value, except for falling through to the next register. So any calls or jumps or returns, they are all RTL transfer instructions. There's an RTL no-op, which does what it says in the tin. It does nothing, but sometimes it's necessary to explicitly generate a no operation. We also have an operation for invalid, which models anytime the disassembler runs into a invalid instruction, the higher levels of the scanner part of the decompiler need to know about this so that they can take the appropriate action. We also have this side effect instruction. Now, side effects are interesting because what they do is they're used to model intrinsic functions that change the internal state of the CPU in a manner that doesn't work as an assignment. So, for instance, if you had an instruction that, for instance, puts the CPU into a sleep mode or halt mode, you would probably want to model that as a function call to a void procedure called halt, and it has no return value. The only reason or the only purpose for this is to have a side effect. So functions that mutate the internal state of the CPU are modeled as side effects. I think that will be enough for now, but there's obviously more detail here. You can talk about that if you have any specific questions. Now, going back to the little sample here, you'll notice that the add instruction, which is a single machine code instruction, ended up being translated into 2 instructions. And so, in general, complex instruction computers like the Game Boy and the Z80 on which it is based, and the x86, which is sort of the archetype of a complex instruction set, they tend to explode into multiple RTL instructions. So here this single instruction became 2. Other processors like the Motorola 68K have such complex addressing modes that they can expand into 9 or 10 RTL instructions. RISC processors like the MIPS or the PowerPC, they tend to be rather less verbose. Every RISC instruction does almost always only exactly one thing, and so they tend to be rather less sparse. But there is a need for gathering the output of the translation of one instruction into a cluster of one or more RTL instructions. And so there is this other class called RTL cluster that we use to sort of bundle the multiple instructions that a single machine code instruction is translated. These are the outputs of the rewriter, which we are about to write. Now, the rewriter, there will be a rewriter for every architecture, and again, the temptation is to steal the one from the Z80, but there are, again, sufficient differences that it makes sense to actually write a completely new rewriter from scratch. So we are then going to perform translations, and one of the things that is helpful in performing these translations is a little handy helper class called the RTL instruction emitter, or RTL emitter, which is right here. Now, this is just a factory class, but it's very helpful because it lets you build these instructions in a manner that is a lot less painful than creating them manually using new statements in C#. And we'll see examples of that quite shortly when we start generating these instructions. Now, One of the shortcuts that I have implemented in Reko, which makes it a little different from most other decompilers, is that I tend to avoid separating out all the separate bits that are set in an instruction when I translate them from machine code. So let's take a look at a sample instruction. Let's take a look at the add. Now, according to this documentation, the add instruction sets all 4 flags of the condition codes. It sets the 0 flag depending on the outcome of the sum. It sets the n flag, which means negative, and apparently is only used by a single instruction, the DAA decimal just after add instruction, which makes it almost completely useless. This is the instruction I'm talking about. The other is the half carry, which tells whether or not a carry happened between the low nibble and the high nibble of the byte. Again, that is only used in the DAA instruction. And finally, there's the C or carry bit. So all 4 bits of this the flag, all 4 of the flag bits are set by this instruction. And the thing is that the code expands voluminously if every single instruction ends up being 8 or 9 statements. So this A equals A plus B would have to be translated into something like this. And then we'd have to, of course, negative equals A is less than 0, a signed comparison. And then we would have to have a half, which would then somehow check if a carry happened. And of course, nobody ever checks. I've never seen any code that actually checks the half carry flag. So we would have to model this somehow. And finally, the carry flag would have to somehow check to see whether A, the new sum, is less than B, because if that is the case, then we have an unsigned overflow. Now this becomes very, very cumbersome. 90% of the time we're not even using the generated code. So what Reko does internally, instead, we summarize these effects. We say, well, A equals A plus B. But then we were going to summarize it so that Z and H and C are set by, and then we use this pseudo expression called cond, which basically says conditionally these flags are set by A somehow. Now later stagers in the decompiler will then do something like this. So suppose we're now checking for unsigned overflow a little while later. In fact, almost immediately after. Typically, this would be the translation of this instruction here, and here we see that the C bit is set by this instruction here, this RTL instruction. So there is an analysis phase in Reko that will locate this, find the uses of all these defined flags, and of course flags that are not used are just discarded, and the end result is something that looks similar to this. It will say, okay, I've got this condition code. Where did it get defined? It was defined here. Well, how did that get defined, this A instruction? Then it looks at the definition of that A instruction and notices that it was the result of a sum. Okay, well in that case, we want to test that sum. So it will then change this to A plus B is less than B. And I'm skipping over a little detail here. In order to this analysis to work, we have to rename the resulting register to something else. Otherwise, we can't test the the results. So this is what the code would generate. So we would do the sum, putting it into a new variable, or a renamed variable, and then the sum of A and B is compared to the, I'm sorry, we compare the sum to the initial value of A, and if A for some reason is smaller, that means that an overflow must have happened in this unsigned addition. Now, we also deal with these things called expressions, which are what we break down all these operands of all of the instructions to. And expression is an abstract base class, and we have lots of expressions. We we need to model so many different constructs from machine code. Let's take a look at a few of those as well before we start. So one key one, of course, is constants. Most machine language programs will contain lots of constants that are, zeros and ones and addresses, and all of these would be immutable values that are in the instructions, and they get translated into this constant expression type. Of course, we have identifiers. Now, identifiers are named things that may or may not be mutable. Now, all of the register accesses, they will be translated into identifiers, but also later phases will translate stack accesses. That is, a memory access where you fetch something from the stack to identifiers as well. This allows us to materialize stack variables and refer to them by identifiers rather than by memory access expressions. We do have to have memory accesses, of course. Most programs access memory, so this instruction or this expression subclass models memory accesses, where you specify the expression for the address, the effective address, and what data type the memory access is. And so you can probably see how you can build up complex expressions from these building stones. And there's quite a few primitive operations modeled here. I'll bring up slice and convert as well because they are interesting. Now, slice models something that does not exist in the C language explicitly, but it is very useful to model operations like when you are reading from a register and storing it to memory on an ARM, for instance. The ARM processor has this instruction called strb, which stores a byte. So you specify a register, and then you specify some destination memory address. And what's going on here is that we want to take the value in R1 and only store the byte part of it, the lowest 8 bits. And to model that in the RTL language, you would write something like this. We have a memory access of R2 of size byte, and then what we're going to be storing is the slice of this R1 register of size byte starting at bit offset 0. So what we do is we take the R1, which is a 32-bit quantity, and we extract the lowermost 8 bits, the byte, starting at bit position 0, and then that gets assigned to the memory. A normal str instruction would not need a slice, it would just do the store immediately. Okay, so these are some of the details that we're going to have to work with once we start working on the rewriter. Now, I think we're ready, so I'll discard this file and we'll start with a rewriter. Now, there are many architectures in Reko, and they all have their own rewriters, so I'm going to be following the pattern that has emerged after all these years of how to best write a rewriter. I'm doing this out of rote, basically. It's almost second nature to me now, but I'll try to do it a little slow so you can sort of follow along with the reasoning. So a cheap way to detect what I need to do now is to just start the the project and try to perform a scan. And Reko needs a functioning rewriter to perform the scan. So we will quickly get an exception because we haven't implemented it yet. The scan is done by loading the binary and then selecting scan binaries. Now what this will do is it will do a recursive disassembly starting at any entry points that we may have defined. And remember, last time we defined a single entry point at address 150. So this is where it will start. It will actually it was 100, wasn't it? So 100, but 100 is a no up followed by a jump, and then we proceed on to the rest of the ROM. So if we try to do that now, we'll get a failure because we haven't we haven't even implemented something called a processor state. Okay, so I'd forgotten about that. We'll need to discuss that shortly. Well, let's do that now. The processor state is something that Reko uses to maintain the state in registers while it's simulating the processor during the recursive scan. So not only are we performing a recursive disassembly of the binary, but simultaneously we're also trying to maintain as many constants as we can inside of this class called the processor state. These become handy when we try to resolve jump tables, but they're not strictly necessary. So to expedite this in favor of time, I'm going to create a dummy processor state for this architecture initially, and then I can refine it as we go. But we do need to create one, so let's go ahead and create a Game Boy processor state. And we'll pass in a pointer to the architecture, and of course now we need to implement this class. And the class derives from a standard abstract base class. So all we need to do now is make the warnings go away, or the errors go away. Alright, and I'll rename the variables to follow the convention obeyed by the code base. Here we have a property for the architecture. Let's just spit out our field. Let's make that read only. Now a clone of this useless class will just return a new instance of Game Boy processor state. Alright, now a properly implemented processor state would then keep a set of register values inside a dictionary, but here we're not going to do that. We're just going to always assume that we don't know what the value of the register R is, so we'll just say constant dot invalid, which means I don't know what this value is. Then there are a few methods that are used for they're customizing points. We'll not be needing to implement them here. But these give you, if you have an odd architecture, the chance to adjust stack pointer values. This one is important though. Right before we make a call, we have to implement or create a little placeholder for how deep the stack is at the point where the call is made. So that's called the call site, and here we're going to create a call site, and we're going to give it the size of the return address that we're pushing onto the stack. In this case, when making calls in this architecture, the return value on the stack is always 2 bytes. This processor does not have an FPU stack, so we just return 0. And then we finish the final methods. Again, these are not that critical for most architectures. And then finally, we're just going to ignore any register values that are set. But as you can imagine, if you want to track these values more accurately, you would create a dictionary in this class and then store the values of these registers as they get set, and then you can retrieve them with the get method. So now we've gotten past that little barrier. Let's continue because we want to create the rewriter. We want to focus on the rewriter. The rewriter is implemented as an IEnumerable that returns a sequence of RTL instruction clusters that we saw before. So if at a high level view, when you create one of these rewriters, which rewrites the machine code to RTL instructions, it's responsible for spitting them back as RTL instruction clusters. So now we need to create a new class, and we're going to implement it like this. We pass in the architecture, we pass in the reader, the other arguments, state, and the binder, and I'll discuss these shortly, and then the host. So Let's create the class. Let's create the constructor. And let's now talk about these different entities, the arguments of a rewriter. So when you create a rewriter, you need to first tell it where to fetch the bytes, where it, which it needs to in order to generate the the RTL instructions. And this typically then gets almost instantly fed to a disassembler. So inside the constructor of the rewriter, we're going to create a disassembler. Here's the processor state. So you can make your rewriter sensitive to the current contents of the registers if you want to. We're not going to do that for this architecture, but in some cases, in some architectures, it's actually worth the while. This is an important class. The storage binder is what associates a register or a condition code with a particular decoded environment or scope. So what this will be doing is it will be creating bindings between registers and the scope in which they're being used. Now this is important because typically registers are global. They can be seen as a global variable that any procedure can mutate. But typically when humans write their functions, they think of them in or when writing code, they think of them as functions. And so we have local variables and functions that we need to keep or separate from the local variables in other functions. And so the binder is an abstraction that we use to keep the registers that are used in one function separated from the registers used in other functions. The rewriter host finally is an interface that we can call to get some services from the hosting environment. And what we'll be using it most heavily for is to generate what are known as intrinsics. Now, recall that I was talking about side effects previously. A side effect of a function is something that is modeled not as a raw expression, but as a function call to a non-existent. It's not calling a real piece of code, but we're modeling it as if it were called to code. So in the case of the halt instruction that I was talking about earlier, we'd probably want to model that with a function called halt that does exactly that. And this is the way for the rewriter to call its environment and say, I would like to have a halt function now. So you would pass in the name of the function. You'd have to pass in whether or not, and this is a misnomer, idempotent is actually not the correct word for it. It should be is side effect free. Sometimes we model complex functions like square root or logarithm this way. So if the function you're defining has no side effects, then you would pass true here. If it does have side effects, if it reason for existing is a side effect, like the halt instruction, you would pass in false. Functions that have side effects typically don't have return types, although they can. Functions that do not have side effects typically, obviously they're evaluated for the return type. And finally, this function can have 0 or more arguments depending on what it is supposed to do. So now that we have created our rewriter class, let's take a look and see how we implement it. So let's make this public, and then we're going to need to implement the two methods of IEnumerable, which are the get enumerator with a generic return type, and then the little brother, the the .NET Runtime version 1, which we'll just implement as a call to the strongly typed one. I can forget about that one now. So, as I mentioned earlier, we are going to create a disassembler in this constructor, and then we're going to use that disassembler to disassemble inside this get enumerator and keep disassembling until we hit the end of the memory. The caller typically, though, will be looking at the instructions that we're spitting out, and once it reaches an instruction like a jump or a return, it's going to want to stop, because a jump stops the flow of instructions. So let's create the disassembler. And the disassembler is called Game Boy Disassembler, and it needs an architecture and it needs a reader. So now we are disassembling. And also what we're going to do is we're actually going to instantly create an enumerator out of that. Recall that a disassembler is actually a class that implements IEnumerable of machine instruction, but now we're actually going to enumerate and get this to be an IEnumerator. And we'll just call it DASM. That's our disassembler. And then we're also going to want to keep track of any intermediate RTL instructions that are being generated from the by translating the machine code instructions into the RTL instructions, and they need to be kept in an array. So let's just or a list. Let's keep a list. I'm going to call it insters or RTLs maybe, and that's going to be a new list of RTL instruction. And then we're going to create an instance of this handy emitter class. And what it needs is a place to store the RTLs that it generates. So I'm going to make this read-only, and the disassembler read-only as well. In fact, let's make them all read-only. So the procedure is going to be we are going to read an instruction from the disassembler, and then we're going to do a big switch statement to see what instructions is this, and then depending on the type, we will then dispatch to different functions that will perform the actual translation, and they will be using this emitter in the that we have a reference to in the M member variable to actually emit the RTL instructions that we want. So what we need to do now is write the getEnumerator method, and this is going to become an iterator, a C# iterator. So what we'll do is we'll do a while loop, and we will say while m.moveNext, dasm.moveNext. So this will then call the disassembler and ask it, please disassemble one instruction, and if that succeeds, then we have an instruction. Otherwise, we'll just fall out of the loop, and the caller will then know that that's the end of this stream of instruction clusters. Okay, so now we need to have an instruction, and I'm going to make this instruction be a member variable, and the reason for that is because I want to avoid passing the parameter everywhere. It's just less typing. So we'll store that as a member variable, and we get it from the disassembler, which now is positioned on this disassembled instruction. We need to create a member variable for this, and this needs to be a mutable member variable, but that becomes a problem with C# 8 because I'm using nullable in this project, and if you put an instruction here and you don't initialize it, you're going to get an error saying you haven't initialized this non-nullable field. So I'm going to trick the compiler here by saying, you know, trust me, just put a value in there and be quiet. It's very unlikely that somebody would ever, in fact, there are no other public methods on this class. The only thing you can do with the rewriter is create one and then call getEnumerator. And almost the first thing that we do is we initialize instructions. So this is actually safe. Okay, so now that we have an instruction, what do? Well, we want to take a look at its mnemonic to see what kind of beast are you. And depending on what the mnemonic is, we do a different thing. So one pattern that I see all of the time is, as I develop this, is I seldom manage to do the whole implementation of one architecture in one go. I tend to do this incrementally, so I need to handle instructions that I have not yet created a rewriter for. So what I typically do in my projects is I create a method called emitUnitTest, which is very handy because what this will do is it will generate a unit test in the output stream that I then can use and basically paste it into the unit test project and then have it run. And now I can guide the development of my of these rewriters based on what actually is occurring in the binary. So very rare instructions will not appear very quickly, but the most common ones will be appearing quickly. I will get a unit test for them. I then make the unit test pass, and then I can continue. I'll demonstrate this in the coming hour. So we emit a unit test, but that is not a, I don't know what instruction that was because it's being handled by the default handler. So what I'll typically do is I'll say to the emitter, hey, I don't know what this was, so I'll just call it invalid. And then I'll mutate the instruction class and tell it, I don't know what that was, so let's just pretend it was an invalid instruction. And then we're done. So that's how we translate the default instruction. Now let's write another translator. If we do get a invalid instruction, then clearly that is something that we can handle immediately. So we'll do the same thing. We'll say invalid, and then we do the same thing that we do in the default case. So why don't we do this? Let's use the go to case syntax of C# to save ourselves some code. And now we're good. Okay, so we will now implement emit unit test, and we can steal the implementation for any one of the other architectures that we have. Let's find a recent one like this one. It has a rewriter. It has an emit unit test right here. And guess what? We'll just take you and put you in here. All right. So what does this emit unit test do? Well, it calls the services, our handy services interface, and asks for a service called test generation service. Now, if you're running the Reko in debug mode, that is built by the debug configuration, then there will be an implementation of iTest generation service available when you're running the unit tests, and also when you're running it, when you're running the actual program. If it's not present, then we'll get a null pointer back, and then this next call will do nothing because we're using this nullable dereference syntax in C#. But if it does exist, then we can report that we don't have a rewriter for this instruction. What we can do then is use a handy prefix. So we'll use this, the Game Boy rewriter prefix, for the generated unit test. All right, so if we run into an unknown instruction, then we will hit this and then generate an invalid instruction. So let's try this. Let's put a breakpoint right here and see what happens if we now try to perform a... Oh, we have a missing instruction here. Hold on a sec. Ah, yes. This is a get enumerator method, but we have to actually yield something. That's kind of important, isn't it? So what we do is we say yield return, and then we take the list of instructions that we had collected in our emitter, and we create a cluster out of them, passing in the address of the cluster, which will typically, but not always, match the address of the machine code instruction. We pass in the length of that machine code instruction, and then we pass in the instruction class like that. And then we have to remember to reset our list of instructions, RTL instructions, for the next iteration of the loop. So a little bit of mutable state here, but typically this will not get called in multiple threads, so we're fine. So what this will do then is it will read an instruction, it will try to translate it in our switch statement, it will then emit to the caller a cluster, an RTL instruction cluster, and then once control returns, we will then clear our list of RTLs and repeat until we run out of instructions. And the caller, of course, can choose to continue calling us or stop as they please. So let's try running this now. And we load our file, and we start a scan, and we hit our breakpoint. So which instruction did it not like? No op. It doesn't know how to translate no op, so we're going to have to do that. And then we throw an exception because of reason. It expected something to come back out of here. So clearly we need to implement a NOP rewriter first. So if we look at our file system though, we'll find that where did we put that file? Hold on a second. I've forgotten where the binary is actually located. I need to look that up real quick. So it's located in, okay, environments L. I'm in the wrong directory. There it is. Okay, so when Reko starts scanning, it creates a subdirectory called executable name.reko. And inside there, it dumps the assembly language that it was able to collect so far. And any RTL in a file somewhat confusingly called .dis. That's not a disassembly, that's the actual RTL instructions getting stored there. But then it also generates a file called gameboyrw.tests, which, as you can probably guess, is generated by that test generation service call that we did here. And if we look inside that code, you'll see that it has generated a little C# fragment that we can now use to start building unit tests. So how about let's do that, because that's going to be guiding us in our work now. So you'll see that the unit tests are very idiomatic. They first specify a number of bytes that are going to be interpreted as machine code, and then we run a test, and we say we then have to complete this by write our expectation here. So in this case, we would expect the NOP RTL instruction to be generated when we encounter the machine code instruction NOP. So let's go to the unit test project then and add a new unit test file for this instruction. And we do that in tests, unit tests, environments, Game Boy. And we'll add the unit test here. Like so. And this will use NUnit. And then, as is so commonly the case, we have a handy implementation abstract base class that we can use to save ourselves some work. And it's called let's see, it's called arch.rewriter test base. So almost all of the rewriters in the solution are using this abstract base class. So we need to create a constructor that sets up the test, and the constructor will then create a new instance of our Game Boy architecture. And it will take a service container that this base class provides for us, and we will give it the name LR35902, and then a new dictionary of options, which we will not use because this architecture has no options. And let's make that a field, and then have this property return that field. And the load address similarly will return an address, and we're going to use the same address that we did for the disassembler unit test. It's going to be a 16-bit pointer at address 100 hexadecimal. And now we need to take our unit test, which was over here, and paste it in here. So our expectation is that if you rewrite the NOP machine code instruction, we get the NOP RTL instruction coming back out. Notice that there's an index here that counts up from 0. Had this been a cluster with more than one instruction, we would see them, we would write the expectations for those instructions in a list. I need to check one thing. There is a base class or a base method in the base class called getRTLStream, and that one was recently changed on a different branch. It hasn't made it to the master branch yet, so we'll need to implement a mechanism for taking a stream of bytes and turning it into into RTL instruction clusters. So what we'll do is we'll create a reader, and we'll use the architecture to do that. Create a actually, it's the endianness that creates the reader, and we start at memory area dot base address at offset 0. That's going to start reading. Oh, maybe we can do it this way. Oh, that's handy. Okay. So architecture apparently implements a method that does all of that nitty-gritty for us. All we need to do is point it at a memory address, tell it to start at this offset of that memory address, and now we have a reader of bytes. Then we need to create an instance of that state that we saw before. And then we need to feed these to the reader. So let's create the reader. The reader is rewriter. Begins with an R. So we pass in an architecture, we pass in the memory reader, we pass in the state, we pass in the binder, which is one of the arguments of this virtual method, and then finally the host. So that creates the reader, and then the caller of this will start extracting RTL instructions out of it. Fantastic. So now we're in a good shape. We should be able to test this. So let's see what happens if we try to run this unit test. Now I'm violating a little bit the way that unit tests are supposed to be written. They're supposed to be written in such a fashion that they fail. Well, maybe we can trigger that. Yeah, so they're supposed to be read the first time you run them, and then you make them pass. So let's follow that dogma. And it fails. Good. That was expected. Why did you fail? Because we haven't implemented a NOP rewriter. So now I'm going to actually this will definitely pass once I finish my implementation of NOP. So how do we do that? Well, it's very simple. We just say case mnemonic NOP. If we get a NOP, then we just call a function called rewrite NOP, which is probably overkill, but hopefully the jitter and the .NET runtime will inline this function. And so now we implement rewrite NOP. What does it do? Well, it does one thing only. It says to the emitter, write me a NOP. That will create a NOP RTL instruction and put it in our list of instructions, and then that gets returned in the make cluster call to the caller. So now if we run this, we should have a green bar. Yay, so we have our first rewritten instruction. Now, the way I typically do this is one instruction at a time, because you want to be paying attention to detail. But because this architecture is so simple, I was thinking about a different approach for this instruction set. So what I'm going to do is I'm going to hop back to our disassembly or disassembler, where, if you recall from the original documentation, there's a set of flags. The flags that this instruction mutates are actually specified here. So my thinking is, why don't we take these and generate functions that create the RTL that sets these particular bits, and we can do that very mechanistically by doing a few regular expression transformations on this file. One thing I did notice as I was reviewing the architecture is that it has some few warts. So let's take a look at the add instruction. So here we're adding two 16-bit registers together, and we'll notice that the 0 flag does not get affected by the sum. The negative flag, for some reason, is turned to 0, and the half carry and the carry set bits are set. But if we then look at the 8-bit add, the 8-bit add does set the 0-bit flag. So this means that some instructions have different flag bit sets depending on the size of the word. So we have to pay attention to this. Otherwise, we will not be modeling the architecture correctly. So what we can do then is take all of these instructions that we have here, and we'll do a bit of a regular expression massaging of them, so that we can generate stub emitters or rewriters for each one of these machine code instructions. And again, because there's a bug in Visual Studio, I'm going to have to do the regular expression mashing inside of Visual Studio Code, which is fine. So the idea then is that every single instruction will be replaced by a call to the implementation of a function called rewrite, and then the name of the function, or the name of the mnemonic. Now, there are going to be a lot of duplicates. So what I'm going to do is I'm going to save myself some trouble by renaming all of the places where we have an A or a B or a C, a D or an E or an H or an L. That's not the proper syntax. And if it's a complete word and it's in uppercase and there's a paren after it, then I want to replace that with reg and a paren. So that will replace all of these single lettered registers with the word reg. And the reason why I'm doing this will become clearer later. Similarly, I'll replace everything that is a single register that is followed by a comma, or by a comma, with reg, and that again is done on all the instructions. Alright. Now, every place where I see implicit and some number, I will replace that with num. That will reduce 192 redundant. And when I see MHL as a whole word, I will replace that with mem for memory access. Now this will result in a bunch of redundant instructions that will be identical, and then I can use unique and sort to get rid of duplicates, because right now we have a lot of instructions. We have 574 of them, and we want to reduce that to a smaller number. It turns out that this architecture has about 70 unique instructions that we need to reduce this number to. So Let's go ahead and save this in a file called let's call it unsorted. Let's put it in the temp file. So, alright, so let's go to the temp directory, and then we sort the unsorted, and then we run it through unique, and then we put it in a file called sorted. Alright, so let's see what that ends up looking like. Alright, so there's now quite a lot fewer instructions, so that's good. And we can get rid of a few of these that are not even things that we want to deal with, like that. The rest of them are very regular now, as you can see. Okay, so now let's take all of these guys and put them back in our unsorted list. And now what we want to do is then, for each one of these instructions, we want to generate a stub function that we will then fill out. And we also want to, in that stub function, generate a call to emit, to a function that I'm going to call emit, and then the name following emit will be pattern on these bit patterns. So for instance, let's take a look at the first instruction here, add C. My intention is to create a private void rewrite ADC, which does emit unit test, because we will not have an actual working implementation, and then it will call emit underscore and then Z0HC. That will be a function that we'll have to define, and what it will, so that will look, that can be done with a regular expression, and we will do this for all of our different expressions. Here I also notice that there are a bunch of different add instructions, but these two have the same outputs, so I'll just do like that. So we'll probably need to hang on to the arguments of the machine code instructions, because it looks like, depending on what the arguments are, the bits that they set in the condition codes might be different. Okay, so we'll have to do this now repeatedly for all of these other instructions. So let's write a regular expression to cope. So we'll start at the beginning of the line. We eat a bunch of spaces. We expect, let's turn off that flag. We see a mnemonic keyword, and then we want to capture the mnemonic itself. And then we eat the comma, but then actually there may be a paren immediately after, so we can't eat the comma. So what we'll want to do now is eat everything up to the / that starts the comment. And now we're not happy. Now why is that? Now we're happy. Okay, great. So the first group that we capture is the mnemonic. The second group is the instruction piece, the operand of the instruction, and then finally we'll have a third group, which is the flags that are being set. And let's see here. We'll capture that in another group. And what do we emit? Well, we emit private void rewrite underscore group 1, comment out group 2, and then here's the body of the function, and it will be emit unit test semicolon, and then emit underscore, and then the bits. Now the bits need to be cleaned up. We haven't done that yet, but we'll do that shortly. So if we do that and terminate the line, let's see what that does. That looks pretty okay to me. Let's do another one. Yep. Okay. That looks good. So let's do them all. Boom. And now what we want to do is convert these things into valid function names. So will match emit underscore and then a paren. And then the minuses here are problematic. So in fact, let's do this. There are no other minus signs anywhere in this file, so we'll just replace all minus signs with underscores just to make that aspect a little easier. Now we can make valid identifiers out of these. So if we encounter a sequence of 4 symbols, and each symbol is either an underscore or a 0 or an 1 or an H or a Z or an H, if it's any one of those, followed by a space, followed by the same pattern, followed by the same pattern. So 4 repetitions of the same pattern spaced with spaces. Then we want to replace them with the same patterns but with no spaces between them. Let's check to make sure that works. Yeah, that looks good. Boom. And now we clean up. We say anytime you see an emit underscore and an open paren followed by a space, any number of spaces, and then excuse me, 4 letters and then a close paren, then we want to change that to emit underscore and then, and so now we have syntactically valid function calls. Alright, so this actually looks a lot like valid C#. And then we'll put this inside of our rewriter. And again, we get the indentation weirdness. Not sure why it behaves that way. It's probably a missing curly brace someplace. Of course, it's not happy about the... Oh, I know why. We have too many of these. So let's fix those. We can't do that in here, sadly. In fact, let's just undo this and do it in here. If we find this, we replace it with curly brace, or no curly brace, just that. That will do the trick. Okay. Save that. And let's go back. Alright. Oh, I'm not sure. We select that and then paste that. That's better. So now it's going to complain about all of these non-existing functions. Now, I have to admit, I went ahead and cheated and actually implemented these functions ahead of time because I wanted to save time. So I'm just going to grab the file that I created to do that. It's going to be in here, so no peeking, but I created a whole pile of these functions. So let's just steal them from here. And then we'll paste them in here. Now these will not compile immediately because there are a few things missing. First of all, there are some references missing. But then there are also, we haven't really, we've talked about the flag bits, but we haven't actually represented them in our architecture yet. So recall that I was talking about how Reko treats flag bits in groups. So here you can see how in this particular emit statement where we are setting the Z, H, and C flags to the output depending on what the expression is, and then we're setting the N flag to always be true, or 1. Well, that is modeled as one assignment which actually takes this expression and assigns that to something called a flag group, which is basically just an identifier that is mapped with a binding to these 3 flag bits. And then the same thing for the N flag bit. We map it to this 1, which is going to be turned into true by the assign statement or method call here. Now, we need to define these, and that's also very tedious. So again, I went ahead and created those ahead of time. They're right here. So I'll just copy these into the registers class to save time. So we'll put them under the processor registers. Here we have the flag group storages. And let's see how we define a flag group storage. What we do is we call a constructor and we say in which processor register do these flag bits live, and in this case they live in the AF register pair, and then we need to indicate which bit of that flag register is this carry bit, and so we'll see later there's an enumerated type that we're going to use where that value is specified. Then we need to give this bit or flag group a name, and finally its data type. Now, because this is a single bit, it is a Boolean, but groups of bits, they are modeled as bytes in this processor architecture. Let's grab the flag M, which is the flag masks for each one of these different flags, and as you can see, I've already done that work as well, and this is based on the manual where they specify where these bits are defined in the AF register, and we can take a look at that documentation real quick. So here we can see that bit 0 is all the lower bits are blank, then bit 4 is the carry, then the half carry, then the subtract flag, and then the 0 flag. So those bit positions correspond to these numeric values. So now that we've done that, we've saved ourselves some trouble. Let's go back to the rewriter now, and let's see, we have some errors here. Okay, that's because Visual Studio got the wrong expression type. Let's fix that. It's we have an unfortunate conflict. Expression is defined both in system link expression and Reko core expressions. What can you do? Okay, so now that we have those defined, we already have one. I guess we do. All right, well, let's keep the one up there. And now we have a bunch of errors remaining. And these are all the duplicates. So we're all very close to actually generating this, but we have to get rid of the duplicates. And this, unfortunately, is a very manual step because we have to take a look at every single instruction and see what is it. Does this match up with the other one? So you can see here that this add carry is a duplicate. This add carry is a duplicate. This add carry, but this one, this add is not. So depending on how you're adding, here there's a difference in the bits that are set. So we'll comment out this function, but we'll have to remember to implement that correctly later. This is a duplicate, so we'll comment out those. And here's yet another. So there's 3 different ways to perform an add on this processor. That's really interesting. And all look the same, so that's fine. All the bits look the same. Yep. All the calls, they don't set any flags at all. In fact, let's put this as a placeholder. We will then remove this emit nothing, which does nothing. And so I'll have to grind through. Oh, here's one missing. That's interesting. I guess we can just create that. Oh, maybe that's just a missing 0 in the... No, it's different. It's underscore 00C, so we need to create one that looks similar to 00C. Oh, but there it is. I'm not sure why that's not matching up. Oh, it wants a parameter. Oh, I've made a little boo-boo here. Some of these take expressions and some of them do not. So we need to inject those. And E, of course, is not defined. This is going to be tedious. Let's do this. Let's just find all open-close pairs. And again, we can't do it in here. We'll have to do it in here. We will go in here and find all the places where we use open and close, and then we'll capture the bits like so, and then replace those with $1 E. Let's see how that fares. Alright, this will still cause a problem because some of these will not take any arguments, but instead of E, let's just fool this by passing in a null, and we'll clean this up later as we work our way through these. So alright, that will be better. So, and tell you what I'll do. I will just comment out the majority of these because we're running a bit short on time and I don't want to bore you with this rather tedious process. So I'll just comment this out. But I know that we see a NOP and I know that we have a jump coming up. So we'll need to leave the jump opcode exposed. And so none of the jumps modify any flags, so we can probably just get rid of that. So they're all going to be same, but we do need to handle the two different cases. Sometimes we jump to a memory location, sometimes we jump to an absolute address, and then sometimes we jump based on a carry. So we'll need to handle those cases. And then the rest we'll do at some other point. Okay, so now we have, let's comment these out. We have implemented NOP. The next instruction I know is a jump, so let's implement the jump translation. So how do we translate jump? Well, first we want the unit test for it, right? So we'll get this into a state where it builds, and then these guys are all blank. Great. So it now compiles. So let's try running it and see what unit tests we get generated this time. And we'll now navigate to the correct directory, get rid of the old file, and then scan. And we hit our breakpoint. We can probably remove the breakpoint now. We don't need it. Okay, so what do we get? A new file. And it has a unit test for the jump instruction. Great. So let's grab that and put it in our unit tests file here. And so what does this translate to in RTL? Well, this is a very simple function. It has no side effects. All it does is it jumps to this address. So I'm going to change this to use the address that we set up in our unit test. We're saying that all of our instructions will start at 0, 100 for simplicity. And this instruction is 3 bytes long, and it takes one it will result in one RTL instruction. So that will be a go-to. That's what it's known in RTL, and it will go to this address 0150. Well, let's now run the unit test, and it will fail because we haven't actually implemented the jump translation. So while that runs, let's go there and find our switch. And so when we encounter a jump, we need to call rewrite jump. And let's go to that function now. And remember that we have to be sure that we check to see whether this function has one or more parameters. Because if it has one parameter or operand, then it's an immediate jump. So we'll check to see if the instruction operand's length is 1, then this is an immediate jump. There's no condition code involved at all. So then we say emitter, do a goto to the first operand, but we have to convert the operand from an expression, or from an operand into this expression type. Let's write a function called op, which takes as an argument the index of the operand that we want to translate into expression, and then we're done. So that's what we need to do. But we need to implement this op function. So op will return an expression, and it will accept an integer, which is the integer of the operand. And the operand then is instruction dot operands iop. And then we do a switch on the type of this operand. And I happen to know that the type of the operand in a jump instruction is the address operand. So if we get an address operand, then we just return the address that is baked into the operand. Now if we don't know what this thing is, then we'll throw an exception, I guess. Or, yeah, let's throw an exception. Throw new not implemented exception. Unimplemented operand type, and then the type. So op.getType.name. Nice. Alright, so if we now run the unit test again, hopefully this will now pass. So as you can see, this is an iterative process, and the reason why it has to be done this way is because every instruction will have semantics that have to be followed pretty closely. And unfortunately, a lot of the instructions are going to be arithmetic instructions like add and subtract. But then we have the instructions that are specific to a particular processor that may require a consultation in the manual, and that is what takes a lot of time. Oh, wow. Okay. So this is something I have completely neglected. We probably should address. It's complaining that this instruction is emitting a little t here. The t stands for transfer instruction. So when we call the m.goto, it creates an RTL goto instruction. And an RTL goto is a transfer instruction. The t there stands for transfer. But our unit test that was automatically generated for us calls it L, which means linear. That is instruction that will be carried out and then flow goes on to the next instruction. So we need to fix our unit test here. But also, the whole cluster also needs the same indication. And we don't have an indication. This is lying and saying this is a linear instruction. It's not, it's a transfer instruction. Well, but how do we get the cluster to have this bit? Well, when we generated the cluster, we were using the instruction class of the machine code instruction itself, right here. And we have neglected to set jump up to properly send the instruction class. So we have to go back to our disassembler and make sure that the instruction classes for the instructions that are doing jumps are correct. So here, for instance, we have to say that this jump has a instruction class transfer. And this guy's not only a transfer, he's a conditional transfer. So we have to set him to conditional transfer. And I'll have to do this for all of the other instructions here. I'm not going to bore you with it, but it is important to properly denote these instructions with their appropriate classes. So in a future commit, you will see me implement this for all of the disassembler instructions. But for now, we fixed it for jump. Jump does need to be correctly implemented here, otherwise we'll get errors later during the decompilation process. So let's fix all the jumps. These are all conditional. This one is not. This one's a unconditional jump. Are there any more? That one, that one. Got them all. All right, let's go back now to our rewriter and run it again. And now hopefully we should be good to go. Great. So now if we run the program again, Reko will pick up on the fact that this is a goto, that is the translation of the jump instruction to a RTL goto is handled by Reko, and it will then, when it scans the program, it will then start scanning at address 150. So let's review that again. Here we see NOP followed by a jump. When we start scanning, we will be translating NOP into an RTL NOP. This JP gets translated into a goto, and Reko knows that if you encounter a goto, it must shift focus and go over to 150. So what is on 150? 150 is a disable interrupts. Now this is one of those side effect functions that I was talking about earlier. DI does not correspond to any expression in the C programming language, for instance. It's a function call. That's the best way to model this. So we will do that. So if we now scan the binary, we will get a unit test for that. So let's see what that unit test looked like. There it is. So we'll just grab that and put it in our file here. And you don't have to be that terse when we're generating C code. So I'm just going to call this disable interrupts. Alright, so now we need to generate this. Now this is a linear function because after the execution of DI, we go to the next line or the next address. So it's a linear function. So now we go to the rewriter and we find DI, which is hidden away over here. So we'll start working on its the writing of DI, and it's going to be trivial. Well, not trivial, but simple, straightforward. We no longer need the unit test, and what we can do is we can say and we don't need this either because we're not setting any flags. We're just going to call the side effect method of the emitter. That is to say, this following function is called for its side effect only. We don't care about the return value. And then we call the host and tell it, I want to use the intrinsic function whose name is disable interrupts. And this is not, this does have side effects. So idempotent is a misnomer. It should be called has no side effects, and That is not true. This one has a side effect. It mutates the state of the processor. And then we need to specify the return type of our function, which in this case is void. It has no return type, and then it takes no parameters. So we're ready. So there's our implementation of di. Now let's see if that works. While that is grinding on, I'm going to take a look at the load. Load is very simple, and I think load is going to be the last instruction we're going to do this time, because I'm running out of time. Oh, we have a syntax error. Let's fix that. Okay. So we have to, of course, go to the switch statement and call this guy. Forgot about that. And now if we run that, oh, we also need to fix the address, because the unit test is using an address based on where it was in the original binary, but all of our unit tests are always based at address 100, so we need to remember to fix that. I can't stop the test. Now I can. Let's run it again. So as you can see now, this looks more like a high-level language already. We're using the goto keyword from the C language. This di instruction is being modeled as a function call. So that's one of the benefits of doing this, is we're raising, well, making it possible to analyze is of course the important one, but also it makes it a little bit more legible. Now let's try running this again, and there should be a load instruction after the first di that we encounter. And after we've implemented that, I'm thinking of calling it a day. But moves are important. A high percentage of the instructions in this binary are moves or loads. So where's 150? Let's just go there. We have the tool, why not use it? Yeah, so there's a bunch of loads that are going to be copying register to register. So we'll need to be able to handle operands that consist of registers. So if we now run and look at our, we'll notice that the next instruction now is load. Okay, great. So excuse me. Now let's grab this unit test and fill it in. Now I know that load does not change any flags, so we can implement it without having to set any flags. So what we want here is the RTL equivalent of this load, which is going to be simply d is assigned with the value of a. So that's pretty simple. We'll also fix the address. All right, and then we now, to follow the dogma, will run the test to make it fail, but while it's executing and building, we will go to our rewriter and we'll implement support for LD. So LD will want, wrong line, doesn't matter, we can swap them. LD is down here somewhere, and there's a lot of LDs, but as you'll notice, well, look at that. This is interesting. There's actually one LD instruction that does change the condition codes. How sneaky. So let's take a look at that. Is that truly the case? was it? LD HL. Okay. Yes, look at that. So it really does, it sets all the 4 flags, 2 to 0 and 2 others to the outcome of whatever this plus does. That's really odd. I wonder why they decided to do that. So that means we have to be aware of that when we write our unit test. So we'll probably need to write a unit test for that particular case. So we'll have to bear that in mind. What opcode was it? It was F8 plus an extra byte. So we need to make sure we create 2 unit tests. One for this simple load and then another one for F8 plus a sequel. Alright, so the expected output here then is going to be, first of all, the assignment, which is HL gets SP minus 4, and that's a signed integer, so we expect it to be a 16-bit signed integer. But then we also have some flags that we expect to get set, and the flags are first the H and C flags. They get set, so we'll have a flag group HC get the cond of HL, and then we need another flag, which is the Z flag gets set to false, and the N flag gets set to false. So how amazing is that? All load instructions except for this one behave that way. Alright, so we go here. Now we need to implement the loader, the load rewriter. And so what we'll do is we'll put both of those in the same package. So we'll remove, actually let's base it on this function right here. And then all the other LDs are going to be the same. So none of the other ones actually, there's a lot of LDs. Wow. Alright, let's kill all of those LDs, because they'll be handled in the same way. Alright, so what is our implementation going to look like? Well, we need to discover whether or not the second argument is one of those strange stack, we call them a stack operand. So what we can do is we say if instruction dot operands 1, that is the second one, is of type stack operand, then we have to set the flags after the fact. Okay, but before we set the flag, we must first create the assignment. So what we do is we say the source of the assignment is, and now we use that op function that we declared previously. We grab the second parameter, that, or operand, that's going to be our source, and our destination is going to be our first operand, and then we create an assignment like that. Then, if the second guy is a stack operand, then we have to call this emit OOHC function, and we're going to use this cond construct that I was explaining earlier, where we say take whatever's in dest and sort of express that some evaluation of that dest is being done, and then assign that to HC. Now in the real code, in any real code, I would probably expect to be highly unlikely that anybody ever looks at these two flags. What does the carry bit mean when you assign from one value to the other? Well, you could possibly have an overflow on the stack pointer. Maybe that's why that's there. But in any case, we will implement that, and then we need to hook up our our switch statement, so that we already did that. Good. And then the thing is, our op is now going to fail. If we try to run this now, op has a switch statement that says, are you an address operand? But this is not an address operand, so it's going to fail. And we expect that failure. So we're going to add a new case, which is the register operand. And if we get that, then we will want to return the register, but we need to bind it to the current function that we're disassembling or decompiling. And we need the binder to do that. So we say binder, ensure that this function has a register identifier for this particular register. Alright, so let's just confirm that, yep, it's didn't have an implementation of register operand. Now it does. So now I run our tests. And I expect the first test to pass, but the second will fail because we need to do a similar thing for stack operand. And we haven't handled it yet. So we can start working on that while the tests are running. Okay. So the simple load is now working, but then the signed the stack operand is not. We need to look at that failure, and it's going to say that it doesn't know how to deal with stack operand, so let's deal with it. Now, let's recall what stack operand was. It has two fields, the stack register field and the offset field, which is a signed integer. And so what we want to do is construct a sum of those two things. And that's fairly easy. First of all, we need to bind the SP, or the stack register. And then we need to generate the add. Now we have a C# integer here, which we can use in one of the overloads that we have inside of our RTL emitter class. So let's integer add is the function or method, and it has a bunch of overloads. The overload that we'll be using is the one that takes, well, actually there's a signed, hold on a second. There is an add or sub signed integer function that is designed for this particular scenario where you have a loose integer and a register, and you want to express that these two are added together. Now let's see. Oh, sorry, it was stack.offset. There we go. So what this will do is it will create an addition expression, and then that gets returned to the caller, and that gets assigned to the assignment. So if we run this now, we should end up with a green test. Let's hope, anyway. Still failing. Alright, that's a detail. Copy and pasted the code, didn't use a unit test that was generated from code, and so I forgot to modify this number, which specifies how many bytes the original instruction was. So this 2-byte machine code instruction, starting at address 010, assigns HL with the stack pointer -4, and it's oh, we haven't tested that yet though. Let's verify that indeed is the case. Another bug. There are 4 instructions generated in this RTL cluster, not 1. So we need to fix that as well. And we have a green bar. Great. So I'm going to put down the pen, so to speak. What we've done today is we've created a rewriter, which is the critical piece of software that raises or lifts machine code instructions into register transfer instructions, RTL, or register transfer language, which is crucial for making analysis possible. Otherwise, we would have to create a separate analyzer for each machine code language, which would be extremely unfeasible. As you saw, there are maybe 6 dozen instructions in this architecture. This would take me about a full day's work to implement. There are processors with way more. Just for curiosity, we can jump over to the x86 implementation of the rewriter, and let's see what it looks like. As you can see, this is a vastly more complex processor. It's so complex, in fact, that I've felt compelled to divide up the rewriter into 6 separate files because there's so many instructions. And here is an enormous switch statement that dispatches based on the x86 instructions. You'll see a similar monster switch statement inside of the ARM rewriters. I mean, there are just ridiculous numbers of instructions here. And this is not even complete. I mean, there are many, many new Intel instructions that I just haven't had the time to implement yet. So almost, oh, look at that. Almost 600 instructions. So this is probably the most time-consuming piece of implementing an architecture, is to implement all of the different instructions and to implement them correctly so that they match the semantics of the processor. Many of the bugs that get filed against Reko are typically because of mistakes that have been made in the translation of these instructions. But once, of course, the bugs are reported, we can write a unit test to sort of forcibly sort of keep the semantics in a well-defined place, and then we fix the rewriter. So here we have completely matched the semantics of this instruction according to the documentation that we have available to us. And then it's just a tedious process of writing the remaining 60 or so. We'll have a rewriter. For my next session, which will probably be on Monday of next week, I'm going to wrap the rewriter up by showing you how to do branches, which are important, and a few more instructions. And then in parallel, I will have implemented all of the rewriters, and so I will then complete the work of the rewriter by implementing all of the remaining rewriters. And we will then be in a position where we can start trying to regenerate C out of the binary that we have. And it will be interesting because it will very likely not work very well initially. And then we can have a discussion about where to go from here. So I thank you all for your time and your enthusiasm. I realize this is a very niche topic, but it's gladdening to see that some people care enough that they will put up with 1.5 hours of rambling from my end. So thanks so much, and see you next time.